if we integrate a constant function, f of xy equals c, on region R, then we'll get c times the area of that region. So we define the average value of f on a closed and bounded region R by the average value of f, and I won't sort of use this notation systematically, just to introduce it, is we integrate f over R and then divide by the area of R. So in other words, this is the, if we let this be c, then thinking of this as, thinking of the integral of f as a volume, so now just let f be anything, thinking of the integral of f as a volume, this is the value such that you would get the same volume maybe a better, we get the same volume by taking just that constant function. So in other words, it's, another way to write this is it's the value c such that the integral of f over R is the same as the integral of that constant function over R. For example, let's find the average value of fxy equals, that got away from us, equals sine of x plus y over the rectangle 0 less than equal x less than equal pi over 2 and 0 less than equal y less than equal to pi. So we need to evaluate, so we need to integrate f over this rectangle. So for this, we don't need to do anything too fancy with the bounds. We just go 0 to pi and 0 to pi over 2 of sine x plus y dx dy. So that'll be integral 0 to pi of negative cos x plus y at pi over 2 and at 0 and then dy. So we need some identities. If we use the identities cos pi over 2 plus y equals negative sine of y, then this becomes okay, so then this will become integral 0 to pi of sine y plus cos y dy, which is negative cosine pi plus sine of pi plus cos of 0 minus sine of 0. These terms go away, so we get 2. So that is the integral of f over this region. And then the area of the region will be pi pi times pi over 2, or pi squared over 2, so the average value of f on this region is 2 over pi squared over 2 equals 4 over pi squared. And so that is this height. And maybe you can see visually, intuitively, that does seem to be the average height taken on by this function on that rectangle. For another example, let's find the average value of f of xy equals 2xy on the quarter circle, quarter disk, maybe I should say, x squared plus y squared less than or equal 1, and in the first quadrant, so x and y are both greater than or equal to 0. Okay, so you want to integrate this. So it will be 2xy, and x and y are symmetric here, so we could do it in either order. We get basically the same calculation. So let's say y goes from 0 to 1, and then x will go from 0 to root 1 minus y squared. Okay, so that's integral 0 to 1 of x squared y, and then we evaluate. So we plug in for x, root 1 minus y squared, and 0. Okay, so that becomes integral 0, 1, 1 minus y squared times y dy. This is y squared over 2 minus y cubed over 3 at 1 and at 0. And that is 3 minus 2 is 1 over 6. Then the area of the quarter disk is pi over 4. So the average value is 1 over 6 over pi over 4 is 2 over 3 pi. So here's that average value, that average height. Now, this is an example. So this area, this is a formula we sort of know from geometry, or maybe we've derived in single variable calculus. So just to tie it to what we're doing now, we can rederive that formula. So if we instead integrate just dx dy over this region, then here we'll be getting, so integral of x. So then that would to find the area using calculus, we'll be integrating root 1 minus y squared dy from 0 to 1. And again, from the table of integrals, so this is not something you should necessarily just see immediately, but it turns out that the integral of root 1 minus y squared is y over 2 root 1 minus y squared plus 1/2 sine inverse of y. This at 1 and at 0. But when y is 1, this is 0. When y is 0, this is 0. Sine inverse of 0 is 0. And sine inverse of 1 is pi over 2. So we get, and then that divided by 2. So that is using calculus, how we would get the area of this quarter disk by integrating just the constant function 1 over that region.